You know, we're starting to sound like a bunch of old dudes.
I was
old fart, that's for sure.
I was just gonna say that. I was gonna say, you know what? That's what we sounded like.
2 minutes.
I just talked to Val. Having a real problem with their dad, and he
Hey,
has to.
Bill, we see, we
Oh,
don't see
boy.
you, we see a black bill, and a black bike.
You get a word in edgewise.
Uh-huh.
You get a word in edgewise.
Okay, guys, I'm showing 7 o'clock here.
Where's our fearless leader?
Well, he's doing the lights for a play or something.
He's hiding.
So the vice president has to step in tonight
Yes, Ed,
and
good.
conduct the meeting. So
Okay.
I'm not even going to try to go to host mode or anything. I'm just going to keep it the way it is now.
Ed.
And, let's see here. Yes, Steve.
Earl and Edie would like to say something. They were kind of having a difficult time getting in.
Okay, go ahead, Earl.
Yeah, Steve, when you were up at Quincy, did you ever go to the Ketty Y?
Nay, did not.
You missed out. That's all I have to say.
Okay.
Okay, I guess first we should start off with the Pledge of Allegiance. I don't see George. Is he on tonight?
Haven't seen him.
There's a flag in the background there. Yeah.
Jeff's got a flag.
I got some.
Flip's got a flag.
Yeah.
Yep, got one too. I could just unroll it, I guess.
First responders.
Hey, there you go. Okay, who wants to lead it off?
I'll do it. I pledge
Pledge
allegiance
allegiance to the
to
flag of the United States of America
and to the
and to the
republic
republic
For which
for which
it
it
stands,
stands
one nation,
nation
under
under
God,
God,
indivisible,
indivisible,
with
liberty
liberty
and
and justice
justice
for all.
for all.
And that's the ideal.
Alrighty.
Hey, Jeff, is that a Trump flag?
Look like it. Fire and police.
First responders.
Yeah.
Okay, let's see here. What do we got here? 1, 2, 3, 4, 5, 6,
Can you do
14, 15, 17, 18. Okay, I show 19. You agree with that, Jeff?
I'm sorry, go ahead, Dave. Sorry, Ed.
I count 19 tonight.
Oh,
How'd you
okay.
get 19?
It's gonna vary. It's gonna, people come in and
Right.
go out. So yeah, it's gonna be pretty close.
Okay, well, we'll start with 19 then.
Okay, sounds good.
I'm counting 2 for one for Earl and one for Edie. So,
Oh, yeah.
Yeah.
Oh, yeah.
okay. Guess we'll start out with Mike, our treasurer. Can you give us a treasurer report?
Yeah, after paying our insurance, we have $5,508.71 in the treasury.
Okay.
Okay. And did everybody read the minutes that Jeff sent out?
Yes, I move that we approve.
Okay, do I have a second?
I
Second.
Okay, all in favor?
Aye.
Aye.
Opposed? Good.
They're
Meetings-
not being.
minutes are accepted. Okay, guess we'll start off with DJ. What's the happening with the director at large, and what's the program going to be?
Okay, tonight I would like to thank Bob for coming to our meeting and giving us a presentation on the ABCs of RFI. Thank you, Bob. And generally, we'll let our guest speakers from outside the club go first, and then we handle the club business after.
Okay. If anybody doesn't have a problem with that, Bob, are you ready to?
Yes, I saw the club treasury's got 5,000 and that happens to be my speaking fee tonight.
Can we owe it to you?
No, yeah, you can owe it to me. Yeah,
Yeah, be a big IOU. Right?
there you go.
Traded for points.
But
Yeah.
I'll sign the check.
No problem at all. That's a pretty good. Our club doesn't have that many, and we got 600 members, I think. And so
Oh, wow.
we're members of the Palomar Radio Club here in Carlsbad. But yeah, I don't think I sent a bio and all that other kind of stuff, so I'll spend a couple of minutes on that. But I'm going to go ahead and share my screen. Let's see if I can do that. Let's just screen share. Okay, somebody's got to allow me to share the screen so that I can do that. So that I'm doing a PowerPoint tonight. It takes about an hour, and it's going to go through a whole bunch of RFI issues that we all have, and hopefully that'll help you prevent that in the future.
Okay, you should be able to do it.
Okay, so right now I can do it. There we go. So how's that? Can everybody see that?
Now we got
Okay.
it.
You got it? All right, there we go. Thank you for permission. All right, so my call sign's AK6R. I was first licensed in '63. I got a novice and a technician at the same time because you could do that in those days. And I was a WB6 QFA and WN6 QFA. And about 3 months later, I passed my commercial license and also got my general. So I've been both a commercial and a ham since about '64, and done a variety of things in my life, run public companies and those type of things. And then about 7 years ago, in fact, we're going to go over that in a second. I might as well just go to that next slide right now. About 7 years ago, a good friend of mine used to live here in Escondido, Jack Althouse, K6NY. Some of you may have known him. He was Kurt Sturba in all of the CQ magazine articles for about 25 years. And when he passed away, he was 93 years old, I believe, at the time. That was 2013, and the entire company was in a 10-foot by 10-foot storage area, down from about at a high peak of probably about 250 people 15 years before that. And what happened was that MFJ copied all his products and had it made in China, and he couldn't compete. So he was basically went back to the ballons and chokes and that kind of business, and did that until the day he died. Practically about a week before he passed away, I saw orders that were still coming in his company. Anyway, make a long story short, my wife and I purchased that company in 2013 and grew it to a multi-million-dollar company over the last 8 years. And our product line consists of Ferrite core products. So we're going to be talking about some of those tonight. Ballons, ununs, speed line chokes, different types of things for either antennas or for decreasing radio frequency interference. We do sell a lot of antennas, off-center feds, end feds, loops, terminated dipoles, and those types of things. And we also have, and I put up on our website, all of the Kurt Sturba articles are free for download on the website. So if you want to download those, you can do that. And we're putting up a couple new ones before the end of the year too. So I'll show you how to get to those in a little while, but you can just put in Kurt Sturba in any of the search bars and it'll come up, and there's no cost to download them. They're pretty interesting. We distribute the products through HRO, Ham Radio Outlet. Have been doing that for a long time, even before we took over the company. And we also sell direct and also on eBay at this point in time. We serve the consumer, commercial, and also the military markets. We do a lot of all of the Homeland Security emergency vans across the nation. All have our ferrites in them. All 363 of them, I think there is. And we did that a couple of years ago. So that's a little bit of history of the company. It was formed in 1965. And it's an old company, but it's got great roots on it and great products and a super name. Everybody, it's been advertising in QST magazine since about 1967, I believe. You can go back and look at all the old products and things. And by the way, all the manuals for all the old products are on the website, free to download. If you have any old Palomar noise bridges or any of those types of things, they're all on there, and you're free to download in the technical section. All right, so let's go talk a little bit about RFI. And there's two aspects of RFI. First of all, are you the source of RFI? Okay. is a picture of my ex-wife on a good day. And it was always the same statement. It's all your fault with that big antenna. You know how that goes. And sometimes you're the source of RFI. You transmit, and if she can't watch Dancing with the Stars or something like that, or it interferes with her stereo or something, boy, you're going to know it right away. And so maybe even you got an award for being really good at RFI, and we call that the Work All Neighbors Award, with special endorsements for 5, 10, 25, 50. This also is a free certificate that you can download from the website, by the way. And I've had over almost 1,000 people have downloaded that, and they've given that away at some of the club meetings and stuff. It's kind of a cute thing, but we came up with that many years ago, and it's worked out pretty good for us. On the other hand, sometimes you are the victim of RFI. And in these days and times, that's more of the case than the reverse, being the source of RFI, because all these electronic devices around us essentially are unregulated. They're supposed to be regulated below 30 megahertz, but nobody gives a darn, and the FCC doesn't do anything about it. And some of the items are your ham antenna, of course, can be a source of RFI, radiating coax, electronic devices. Roku systems are notoriously bad. Anything made by LG, particularly refrigerators, washer dryers, those are very noisy. Solar systems are noisy, and nobody will do anything about them because the people that put them in are integrators. They're not the manufacturers, and vice versa. The manufacturers say we have no control after the integrators put it in, so nobody takes any responsibility for those. Grow lights, particularly in California, you can grow virtually anything these days, and grow lights are a major problem. All the motors in California, any kind of motor in California has to be a pulse width modulated motor. They don't vary the voltages anymore, they vary the pulses to it. And as a result, you've got square waves all over the place for the new air conditioners, for just about everything. And they're very noisy. Plasma TVs, DSL routers, anything with a wall wart that you plug in is potentially a real problem. And we already talked about the washers and dryers and that kind of stuff. And what's the symptom? The symptom is you have a high noise level, and you can't hear the weak signals. There's no DX, no fun. It's kind of a hassle. Now that the sunspot cycles are starting to come back, and 10 meters has been wide open for about the last week, boys and girls, and even into Europe with 100 watts, it's pretty easy. It's time for us to solve some of these problems so we can work some of that DX. So I'm going to go over some of the objectives, what we're going to talk about tonight. And first of all, if you don't know anything about RFI, I'm going to kind of show you what the symptoms are of RFI so you know that that's what it is, how to pinpoint some of the causes, and some real simple cures that'll make operating ham radio a lot easier. And so we're going to talk about what's a ferrite filter, how to choose it, how to buy it, and how to solve it for a particular issue, and how to use ferrites to solve the number one RFI problem shared by all hams using coax fed antennas. How to use ferrites to solve transmitter RFI problems, how to reduce your noise floor and keep your neighbors and their spouse happy. Wouldn't that be just great if we could all do that with one ferrite? But I want you to understand the concepts. I'm not going to put any math in this tonight. This is all concepts, and it's fairly easy to understand. If you've never dealt with ferrites before, if you've heard this talk before, just bear with us. There's always seems to be something new that pops up that you didn't hear last time I did this. I did this same talk for the ARRL section managers and the emergency communication managers. We had 350 people online. I think the Q&A was almost 4 hours long after it. So they obviously had a lot of questions, and I'll stick around for Q&A too. All right, so let's put our thinking caps on and talk a little bit about what is RFI. RFI stands for radio frequency interference. And typically, what do we define as radio frequencies? Usually it's something above about 100 kilohertz. We're not really talking about AC power lines and those types of things. We're talking about mostly frequencies above 100 kilohertz. Typically, switch mode power supplies, everything up from that. And we go up to about 2 gigahertz. That's our frequency range that we deal with. And what it is, it's a disturbance that causes an electrical circuit to function improperly. That's a pretty broad definition, but it's true. Some of the things that it and some of the sources could be sunspots, cosmic noise, lightning, atmospheric static, AC power lines, and those types of things. And those really aren't something that you can do with a ferrite. And we're not really going to talk about those. On the other hand, there's lots of things that are called transmitters, and some of those are obvious to us. That's ham, CB, AM, FM transmitter, commercial radio stations. But all the electronic devices that we have around our house can conceivably be thought of as transmitters. And what are their antennas? It's the AC power lines that they use. It may be the long DSL lines out to the box on the street. Those types of things. We all have inverters all throughout the house with switching power supplies. Computer electronics are notoriously noisy, or can be, and cable DSL and Ethernet can also be a problem. But in general, you can use simple filters to fix that, or at least make that noise go down and not become a problem. Some of the typical victims are basically any electronic device that malfunctions by acting as an unintended receiver of RFI. Okay, so how do you get RFI? And secondly, after that, we're going to talk about how do you get rid of RFI. So RFI requires three things. It requires a source, it requires a victim, and it requires a path between the source and a victim. If you chop out any of those three items, you do not have RFI. All right. And typically the coupling path between the source and the victim is usually it's a wire, but it may not be. It may be a radiation. You're radiating your antenna and your neighbor picks it up, it gets into their wires and then causes an issue with their devices, whatever that happens to be. But it also can be conductive. You're transmitting on your antenna and it gets into the coax line from your satellite system, and the outside braid carries it into your receiver, and you get all kinds of garbage and pixelation and those types of things. It can be inductive. You may have a antenna that's in the attic, for example, and you transmit on that, and it's creating waves. Those waves go into your AC power lines, and then they cause all kinds of issues and stuff like that. If you have touch lamps in the house and you're transmitting very close to them, more than likely you'll see them blink on and off all the time. All right. Or that happened to me when I had a sprinkler system. I would do Morse code and my sprinklers would go on and off to dits and dahs. And my neighbor came over and asked me, "Oh, what's going on with that?" I said, "That's just the unique way that I water my lawn, you see." And a couple of ferrite filters solved that problem, and it absolutely went away. But I was a new kid on the block, and it was a good way to meet my neighbors, I guess. And the fourth way, it can be capacitive. It may be just because you're close, and you may be some capacitive coupling rather than inductive. Most of the things that we're going to be talking about are something that comes on a wire, and it may be the source for that could be actually on the wire itself, or it can be radiation that it gets induced that induces a current into the wire. So what we generally end up spending our time is we can recognize that we have RFI. Now the problem is how do we find the source, and what's the path? How is it actually interacting with the thing that we're dealing with? So we can split the RFI basically into two sides. One is the transmit symptoms and one is receive symptoms, and they tend to be a little different. All right, the transmit symptoms are usually caused by your transmitter or your antenna. All right, so you're doing something, you're keying up, and something's happened. When I was 14 years old, I got my first kiss, and that was from a hot microphone. It was an old D104, and I put my lips to it, and it got burned on a Viking 1 transmitter. I'll never forget that. And it was RFI because I didn't have any grounds anywheres, and I didn't really know what I was doing. But the symptoms are your mic cable, your microphone itself may be RF hot. And usually you'll get a report of distorted audio. That's generally what the other hams will tell you. Hey, your audio is all distorted, something's going wrong. And that just means your audio input stages are picking up RFI and distorting the audio that you're putting into them. A lot of times your antennas just don't tune correctly. There's a high SWR, and it's because your dipole has become a tripole. And we'll talk a little bit about that later on. or your coax becomes part of the antenna system. And if it's close to other wires in your house, it can induce current into those and cause issues. Your voice or your transmission causes interference with consumer electronic devices, and they're acting as ham radio receivers. And what are some of these items? They could be computers, TV audio systems, particularly powered subwoofers are a major issue because they pick up RFI off of the power lines. And if you're on 80 or 160 meters, it's not uncommon to turn on a lot of distortion in powered subwoofers, home theater systems, anything that's got a long wire attached to it, primarily AC power lines. But security systems are the same way. Garage door openers. If you put in the new LED lights in some of these garages, your garage door openers won't work anymore because of the interference caused by the LED lights. And we have a garage door opener RFI kit. In fact, here's an interesting side story. A colonel called me from Oklahoma and he said, "Son, I got a problem." And I said, "Well, what's your problem?" He says, "Well, we put some new radios in our airplanes. And every time we fly over a particular homeowners association, all 100 garage doors go up at once." And I said, "Well, I got it, sir." I said, "Sir, I have a solution for that." So I sold him 100 RFI kits, and he had, at their expense, put them into all the different homes in that association, and it solved that problem. So they didn't go up and down anymore. But those are the typical types of things that can happen. And sprinkler systems, we already talked a little bit about those with my DITs and DAs, but that we have a sprinkler system RFI kit because of that. A lot of the kits that I've designed or put together are based upon customer feedback, things that don't that aren't working for them, but the theory is all the same. It's just a matter of figuring out where to apply it. The spouse alarm goes off. Okay, that's the Dancing with the Stars alarm in my house. And so if she can't watch that and I'm transmitting, she gets to watch it. That's just how it goes. But I've got ferrites over most of the things, and it's not really a problem anymore. Receive symptoms are just the opposite of that. They're caused by sources outside your radio, generally devices that we've just been talking about, but they're acting as little transmitters, and you're picking it up one way or the other. Could be, for example, FT8's a real popular mode these days, but the USB cable going into your computer can be picking up the power supply noise from your computer or laptop, feeding it in, and you're seeing a high noise level, and that's a problem. So there's a quick example. Birdies, chirps, buzzes, clicks, broadband noise on your receiver. If you tune to a 7198 or 14198 and you see that birdie on 40 meters, those are the sun power solar systems in your area. I can track them about 4 blocks away from my place, and I can see that there's a signal there. It dithers back and forth, and it's never on the frequency for more than the FCC limit, but it's there all day long when there's daylight. Turns off at night when the solar systems go off. All right, so let's look a little bit about what some of these antennas are and what the path is. And once we know those, we can apply a Band-Aid or a fix to it to stop the RFI. So when you're talking about receiving antennas, okay, generally a receiving antenna goes along with the length of the interfering signal. So if let's say you're KFI up in Los Angeles, right? And they've bought, I don't know, 1,000 RFI kits from me, and they put them into all their neighbors within about a mile or 2 miles of the transmitter. And but they typically, the problem there is on the low bands is you need long antennas to be resonant at those frequencies. And so what are typically long antennas in your house? Well, AC power lines, you may have 1,000 feet of those easily in your house. Telephone DSL lines or the DSL lines coming from the box out on the street. Satellite or cable coax, all right, those typically 50, maybe 100 feet long, and the outside of that coax acts as a receiving antenna, pulling it right into the system. Long Ethernet cables, antenna feed lines from coax shields, If you're using antenna switches with more than one antenna on it, we'll talk about that in a little while. But if you have an antenna switch with 4 antennas on it, any one time you have 5 receive antennas, and we'll show you how you fix that problem. Believe it or not, the antenna control rotor cables, they typically come right down to your rotor, but they're not really grounded very well. Usually they may have a shield on them, but they still act as pickup receive antennas. If you're on the 2nd story ground, if you have a 2nd story ham shack and you have a 16-foot ground length on your ground rod, that's a quarter wavelength on 20 meters. And I almost guarantee you on 20 meters, you're going to have RFI in the shack, because if you have a ground at one end, you're going to have high impedance on the other end with any quarter wavelength transmission line. So the solution for that is simple. Just don't make it a resonant quarter wave on any band that you're operating on. Make it 18 feet or 19 feet or something like that. It's okay to have extra, but if you have it at 16 feet, I can count probably at least 100 people who have called me with that problem. I don't sell them anything. I just say change your feed line length and the problem goes away. On the other hand, if you're in the FM broadcast band or 20 and anywhere from 20 meters up to about 450, you have to look for short antenna. So what's a short antenna? Well, a speaker wire, device interconnect cables, for example, HDMI cables between your home theater system and your or your Roku box and your TV, short mic cables, short Ethernet cables. They pick up, a quarter wave on 2 meters is only 19 inches. It doesn't take very much to have that kind of RFI. And so you look at, so if you're experiencing RFI on those frequencies, you look for short wires, and the short wires are typically the ones you're going to try and protect. So what do these antennas do? The antennas actually pick up radiated or conducted RFI, which induces a current on all the unshielded antenna conductors from a source. Well, that's a sentence with a lot of words on it. So what we're going to do is kind of look at how the practical application of that is. So let's go to the next slide. So here's an example. There's a right and a left side to this, the red and the green. All right. So on the left-hand side, where the green receiver is, we have a transmitter out there, and it could be anything that we've been talking about. Could be a real noisy router, for example. Anyway, it's putting radiation through the air, and then you have your normal ham radio antenna, your dipole or your beam or whatever it is. It picks up that radiation and induces a current into the antenna. All right. And it goes right into your receiver, and it looks like a high noise floor. Well, the solution to stop that is you put what they call a choke in the transmission line before the receiver, and it actually stops that signal. However, it lets the normal signal go right through. Right. That's pretty cool. Well, and when you have a transmitter and you're transmitting, the opposite is exactly the same solution. If you're transmitting and you do not have a choke in there, you're putting radiation, for example, on the outside of the coax, and it radiates. It may be next to an AC power line or something like that. It induces, which in turn induces your signal into the AC power line, which then affects your TV receiver or whatever it's connected to. And so the solution is simple. If you put a choke in your transmitter RF coax line, it will stop that, and you won't have that issue. And we'll look at some specific ways to do that in the next couple of slides. But the idea is that the transmit and receive are essentially reciprocal. It just depends whether you're receiving or whether you're transmitting, but the solution is very similar. You can use resonant traps. You can use all kinds of filters with high impedance. You can use low pass filters. We probably all remember the low pass filters we used in the 60s and 70s, or at least I do. And they were fine for what they did, but they really didn't stop the noise or anything like that. But ferrites, on the other hand, can solve a lot of those problems that the other items don't. But before we figure out which ferrites to take, we're going to go visit Ohm's law, and I hope everybody remembers Ohm's law. It's E divided by IR. It's that equation on the right-hand side there. By the way, here's a trivia question, which is great if you're sitting at a bar and you want to get a free drink. E stands for electromotive force, right? R stands for resistance. Well, why doesn't I have a C there for current. What does I stand for? That's the question. All right. So I'm not going to give you the answer right now, but to think about what I stands for, and later on I'll tell you what it is. But most guys don't know what that is. And if you bet, you ask somebody if you know Ohm's law, I said, okay, well, yeah, I know Ohm's law. Well, what's the I stand for? All right. And most people don't know that. But once you do know it, it's good for a couple free drinks. Okay, so let's look at EIR. So one way to make the current obviously is equal to E divided by R, all right? So if we shut down the source, if we set E to 0, then I becomes obviously 0. Or on the other hand, if we put a choke in the path and we make R very, very high, and typically it has to be over 1,000 ohms to make it measurable, then I will be smaller. If we make it really big, like 5,000 ohms or 10,000 ohms, then I becomes almost immeasurable, and it goes away completely. And so if you were going to use a choke and you wanted to create very little noise, you would put a very high choke right next to your receiver on your coax line, and it would it could take down 4 to 6 S units at least of noise, of common mode noise. All right. So the objective really is minimizing the current I in the wire that has RFI in it. And so how do we do that? Well, the way we're going to do about in this talk is we're going to use ferrites. Ferrites are our friends, just like the little boys at the bottom right there. So we're going to talk about those and just tell you a little bit is basically the fundamentals of ferrites. If you've never worked with a ferrite before, we're going to show you how to do that. If you have, maybe there's some things that you can pick up. And so we're going to show you how to select, buy, configure, and how you actually apply them. Where do you put them? Where do you put these Band-Aids so they have the best effect? But before we do that, we have to know a couple of things about the shapes of ferrites, because it makes a big difference on how you use them. So there's basically 3 different types. One is a slip-on bead, kind of like it's longer than it is wide, so it's like a little cylinder. The next are snap-on beads. That's the picture in the right-hand side, left-hand side there. A snap-on bead, you put the cable in the side and you snap it on. Sometimes you can put it through more than once, and we'll talk about why that's an advantage. The third type is a toroid, also called a toroid, or it's called a ring. It's the same thing for the same word for the same thing. The ferrites on the right-hand side are spelled differently, and they're not part of the equation, but they're so cute, I just had to put them in the slide. Anyway, what are some of the characteristics of all these different ferrites? Well, usually they're pretty cheap. The rings are maybe $10, and some of the slip-on beads are, they're as low as 35, 40 cents a piece. So the cost is not a big issue. They do suppress RFI from about 100 kilohertz to 2 gigahertz. That's kind of the sweet spot for them. And they work on all conductive paths. So you have to have something that's conducting RFI. That can be an antenna feed line. It can be an AC/DC cable. It can be a USB cable, whatever. And incidentally, you can put multiple conductive paths through the same ferrite. You don't have to have one ferrite for coax and then a different one for AC/DC lines. You can actually put them through the same one, and it will get rid of the noise in both of them. There's lots of options in size and shape and frequency range to suppress RFI currents, and we're going to be talking about those and how you can be smart about what you buy. We're going to show you how they work, how to choose the correct one, and where to install it for a particular problem. Before we do that, we need to kind of go through the characteristics of a ferrite. And it's kind of like talking about what's a resistor and how does it work. And so what we're going to learn is ferrites, they're really frequency dependent resistors. That's the easiest way to understand it. They have a different resistance at different frequencies. All right. And so what you're going to want to do, if you remember Ohm's law, you want to make R as big as possible. So if you're having interference at a particular frequency, you want to choose a ferrite who's got a big resistance at that frequency. All right. And we'll show you how that works. But here's a simple graph of its frequency across the bottom and its impedance or resistance going up the left-hand side. So as you can see here, take my little cursor over here, you can see that from about the brownish area right here, which is about 80 megahertz up to roughly 200 megahertz, it really peaks in reactance, which is also resistance in this case. And so if you were going to utilize this particular ferrite and you had a problem on 2 meters, for example, or you wanted to get rid of some of the issues that you're having on the FM broadcast interference, this would be the type of ferrite that you use for that. Other ferrites have curves in different places, and we'll show you some of those in a second. The ferrites have an equivalent circuit. They're basically a resistor, a capacitor, and an inductor in series, in parallel, and so they work at different frequencies. They're characterized by 3 different regions. One is an inductive region, one is a resistance region, and that's what these different colors are. The blue is the resistance, the inductive reactance is the red, and then the total reactance is the curve on the top. The ferrites must be used, if you're going to use them for RFI, all right, they have to be used in the resistive region, in this right here. If you used them out here at 10 megahertz, they wouldn't work at all right. And we'll show you how some people get sucked into buying stuff that's not in the right region just because it's dirt cheap, but they're just not designed for what you want. So first of all, you have to know what the resistance region is. That means you have to know the specs. You have to know how to read the specs on a ferrite, kind of like a resistor, you know. You have to know what the color bands are, or at least you know what the impedance is. All right. So how can resistance be increased? Let's assume that we have a ferrite. We want to increase the resistance up to a certain level. So let's go to the next slide here. I'm going to show you. You've probably seen these before. On the lower right hand here, these are called coaxial chokes. This one's got 5 beads at the top, then 10 beads, and then 15 beads. And so why would you put more beads on there and spend a little bit more money? Well, here's the reason. This is a graph here very similar to the one that we saw before. It goes from 1 megahertz up to 61 megahertz. And the light blue lines or light blue columns here are the bands. So this is 6 meters, this is 10 meters, all the way down to 160 on the bottom here. So if you look at and this is a graph of basically the resistance. So the resistance for 5 bands, you know, it increases with frequency up to about 10 meters here, and then it's pretty consistent to at about 1,000 ohms all the way across. On the other hand, if you put more than 5 beads, you put 10 beads, guess what? It gets higher. Just like a resistor, they add in series. So you go from 5 to 10, you get higher resistance, right? If you take a bunch of 10 ohm resistors and you put them in series, you're going to get 10 plus 10 plus 10 plus 10 plus 10, right? However, remember they're frequency dependent. So they change resistance with frequency. They're not constant like a typical resistor. If you have 15 beads and you're working, let's say 160, 80 and up all the way up to about 30 meters here, this would be a much bigger choke, a much better choke than you would if you're just using a 5 bead one. All right. So if you're experiencing a lot of RFI issues, and it would be better to get more beads than it would be to get less beads. All right. So you've seen these different ones, but this gives you an idea. So at 7 megahertz, we'll just take a 7 megahertz picture right here. 5 beads is 400 ohms, 10 beads is 1,000, 15 is 1,600. The general rule of thumb is you need at least 1,000 to have any measurable difference. All right. So 5 beads, if you put it on there, you're not going to see much difference. You won't be able to hear the difference, or it's very hard to measure it. But at 1,000 ohms, now you're starting to get, you're starting to get a half of an S unit to an S unit of noise reduction. And once you get up to 5 or 10,000 ohms, you might see as much as, 6 S units of noise reduction. All right. But you can't do it with putting these beads unless you put 100 beads in a row. And that's financially uneconomical, and there's a better way to do it too. So what's the better way to do it? There's 2 characteristics of ferrites and how they increase their impedance. Because they are essentially an inductor in parallel with a capacitor and a resistor, if you put multiple turns through the center, it increases the resistance according to the square of the number of turns. Okay, let me say that a little bit differently. If you put 2 turns through anything, all right, you take, here's an example of 1 turn down here. Here's an example of 3 turns. I take the wire and I put it through again, and I put it through again. It will have not, that's 3 times. So 3 squared is 9, right? So it will have 9 times the effectiveness of this one over here with 1 turn. All right. So it's a lot. Or saying it a different way, if I put 9 of these in a row, it would be the same as having just 1 of these with 3 turns. All right. So it's much better to get a ferrite with a little bit bigger hole in it than the cable size, so that you can put it through multiple times, because you'll save a lot of money. Right. I mean, this is a $6 solution, and these are like $3. They're $3 a piece. And so if you had 9 of these, you'd be spending $27, but all you got to do is spend $6 and put 3 turns of wire through it, and you have the same exact effect. You save money. Well, let's go one step further. Here's 7 turns through a big ring. All right. It's almost 6,400 ohms. All right. It's incredible. So you can always save money. And the thing is, you have to have the size of the hole. In this case, in the far right-hand side here, we chose a big enough hole so that the plug would go through without having to take the plug off. All right. So if 1 turn is equal to R, 2 turns is 4R, 3 turns is 9R, which we just talked about. The general rule is you need at least 10 times the line impedance. So an example would be if you have a 50 ohm coax, you need to get at least 500 and preferably 1,000 ohms of choking at the frequency that you're operating it at, in order to have it be effective. Okay, so there's one more concept that you need to get here, and that is, how do you choose the correct RFI for the correct frequency? All right, we know now that if you put more turns in it, or you put more in a row series wise, it will be more effective. There's nothing to say that you can take 3 turns on one and then right next to it put another one with 3 turns. Right? It'll be twice as much. It won't be the square or anything like that, but it definitely will increase it. And there's some tricks to how we can make that work. So there's one more concept here. And the concept is that the mix, or the compounds that make up ferrites, change depending upon what they call a mix number. I use mix number because that's what Ferrite Corporation uses. Other companies use they use a composition number or a number, for example. So remember, we saw that graph before where the resistance went up at certain frequencies. Well, what is available now is there are different types of ferrites with different chemical compositions, and those chemical compositions determine where the peak is. All right. So for example, this one happens to be a mix 75. It peaks right around 2 megahertz. It's a wonderful compound to use on 160 meters. All right. Some of you may have heard of mix 31, which is real common in all the ARRL publications and things. And it's not as good as mix 75 until you get about 5 megahertz. At 5 megahertz, then mix 75 tails off, and 31 goes all the way up to here. On the other hand, when you get up to roughly 200 megahertz, 250 megahertz, mix 61 is much, much better. All right. Unfortunately, one of the challenges that we have in ferrites is that not all sizes and shapes come in all mixes. All right. So, for example, with mix 31, you can get a 4-inch wide ring, but you can't get that ring in any other mix. But the ring is very, very good if you have a super big plug, like a generator plug, or you have a dryer cable plug and you don't want to cut off the end of it. You can just put that cable through because it's got a 3-inch inside diameter. But you cannot get that in a mix 75. They just don't make it. So you have to kind of mix and match the different mixes in order to find a shape that works. All right. We've done a lot of that homework for you, but I'm just telling you, you can't get all sizes and shapes in all different mixes. Mix 43 is the one that's been out forever, since practically World War II, and you can get virtually every shape and size in that. Mix 75 is a later one. It's only been out for 10 years, but it's a wonderful mix if you have switching power supplies, wall warts, those types of things. It just suppresses that current so well. Right down in the 100 kilohertz to 1 megahertz, which by the way is where all the solar systems operate too. And so we have solar system RFI kits that use mix 75 on every one of the panels, and it takes care of the little micro inverters on every panel. It just quiets them down. You can't even hear them anymore. So the concept here is that there are different compositions, and you have to choose the right composition, as well as the shape, as well as the number of turns that you can use in order to maximize the resistance for what you're trying to accomplish. The most popular mixes that you'll find are mix 31, 43, 61, and 75. And I'll be talking a little bit about those and show you some practical applications of how to use those. If you select the wrong mix, in other words, if you got a problem here at 20 meters and you're using mix 75, it's one turn is only going to be 50 ohms. You're going to have to try and put 10 turns through something. There's no mix 75s that you could put 10 turns through. They don't even make it, right? But if you're using it on a piece of coax, for example, a 1/4 inch RG8X, which they do make that size, you'd be much better off to use a mix 31 or any of the other mixes at that particular frequency. All right. But if you're trying to filter something down here at 160 meters, 75 is almost what? It's almost 4 times, 5 times better than mix 31. So you got to know what to shop for. So before you know what to shop for, I'm going to tell you how not to buy ferrites. Okay. And this is a trap that a lot of people fall into. All right. So if you go to Amazon, you go to eBay, you go to a lot of different these websites, you'll see a something similar to this. It says buy a pack of 20, $9.95, all right, or $19.95, whatever it happens to be. It's cheap, all right. It gives you all these different ferrites. There's only one problem, the problem is there's no specs, all right. They only say 1995 ferrites will solve all your problems. That's it. They don't tell you what the mix is. They don't tell you what the resistance or the impedance range is, all right? There's no frequency range which they're good for. And I will tell you, most of these come from recycled video cables that are sent over to China. They take them off, they put new outsides on them, and then they repackage them, and they send them back here as dirt cheap ferrites that you can buy. They mostly will not work in anything except video frequencies, up in the 100 to 500 megahertz range. So if you're trying to use these to solve a problem in the ham bands, good luck. You may have to put 30 or 40 in a row just to get any kind of response at all, if they work. Ditto with anything you buy at swap meets, unless you know what they are, or unless you buy my stuff at a swap meet. And I'll be at TRW, by the way, this Saturday, and I'll have some ferrites there, as I usually do. The bottom line is don't buy them. If you don't know the specs, it's like buying a resistor without a color code on it. All right. It's big, it's ugly, but you don't know if it's 100 ohms, 10 ohms, or 1,000 ohms. And if you don't know what they are, you're just wasting your money. Okay. So we all know about truth in labeling. So what's the alternative? Whenever you buy anything from us, and you can look through our entire website, we always tell you, first of all, what the dimensions are, what the mix is, what the RFI range is, of course, what the part number is. But here by megahertz, 5, 10, 2500, 250, this is what the resistance is for one turn. So if you have a problem, let's say on 30 meters, and you want to solve that problem, every turn that you put through this particular ferrite has 100 ohms. And so you need at least, if you put 3 turns through it, you have 900 ohms. It would solve the problem because you're pretty close to 1,000 ohms. All right. On the other hand, if you're up here at 2 meters, it's roughly 260 ohms. You only need about 2 or 3 turns on a J pole, for example, and that's it. It's all you would need. You would only need 1 ferrite, right? So basically, when you're using ferrites, look for the specs, and if you don't have the specs, just avoid them because it's a waste of money. You really need to know what those are. And I'll make one more thing here clear. There are certain ferrite mixes that are good for RFI, and there are certain ferrite mixes that are different, or they have a different frequency response if they're used for inductors. All right. So if you're using it for a balun, for a 4-to-1 balun, for example, or a 49-to-1, because you see a lot of those for the end-feds antennas and stuff. The frequency range for using as an inductor is completely different than the frequency range if you're using it for RFI purposes. All right, just to be aware of that. All right, so if you're use it for RFI purposes, know the specs. All right, so here's a quick recap, and then we're going to go into some actually practical applications. You want to determine the RFI interfering frequency if you can. All right, a lot of times you'll be hearing the harmonic of the frequency. That's real typical with low frequency wall warts and those types of things. You're hearing the power supply, but you may be hearing the fifth harmonic on 80 meters, or maybe even on 40 meters. And you have to filter the fundamental, not the harmonic. Right? Choose the proper mix. Right? Right? Choose the correct topology or shape. Are you going to use a slip-on, a snap-on, or a ring? In a lot of cases, you may not have any slack in the line, and there's no choice. You got to use a snap-on. You got to put 4 or 5 in a row. All right, but you want to use it to fit the path. Install the ferrites on the path, and then retest it to make sure it's working. All right, either your noise level is going down, or you're not interfering with whatever you are transmitting. And use additional ferrites or paths if the RSI persists. It's not uncommon for your transceiver, for example, to be putting RF out not only on the coax line, but it may be feeding it back through the DC power supply. It may be feeding it back through the USB cable going back to your computer, which in turn is going through that and getting into your AC power lines that way. So all RF does not go out to coax, even if you've got grounds and all that other type of stuff. Okay, the most popular mix for HF, that's basically 160 meters to 6 meters and up to 2 meters is mix 31. You'll see that in the literature all over the place. Mix 75 is for low frequencies, switching power supplies, anything below about 5 megahertz. And mix 61 is good for 200 to 2 gigahertz, right? So let's talk about, now that we have some kind of fundamentals behind us, let's talk about how we use these filters if you have transmit RFI. In other words, you're causing the problem. So I'm going to talk a little bit about some solution kits. A lot of this is over the head of people where they don't want to try and figure it out. So what we did a long time ago is said, you know what, we're just going to come up with solution kits. You buy the kit, you put it on, problem is solved. Right? You don't have to figure out all the resistances and turns and all that kind of stuff. We just show you how to do it, and you buy it and fix it. So we're going to talk a little bit about RFI kits for HF transceivers and amplifiers. How do we minimize coax cable radiation? And how do you install solution-specific kits for particular victims? And a victim could be a subwoofer, for example, or you may be transmitting and your computer's slowing down because you're messing up your router. So the first thing we want to talk about is transceiver kits and RFI kits. And what you want to do is minimize the source. You are the source, you're interfering with somebody else. And so let's get rid of some of the antennas that are hooked to your radios and stuff. Typically, if you have a transmitter, an amplifier, and an antenna, those three react together. You need to choke all the cables into and out of the radios, generally the amplifier and also the antenna tuners. This includes all coax RF feed lines or common lines or the common line of a coax switch. I'll talk specifically about coax switches in a couple slides, but just know that the coax has to have a choke on it, as well as the rotor and antenna control lines, AC/DC power lines, including the wall warts, computers, all the radio interconnects, AC power, and I'll show you some specific examples in the next pages. But basically, anything that's got a wire coming in and out of your radio or your equipment needs to have some type of choke on it to stop, to act as a stop sign that says, don't come this way. All right, when you install it, the problem is usually solved, or it's reduced so that it's not a measurable function. So let's look at some transceivers. So on the left-hand side, you see an ICOM 7300. It's the same one on the right-hand side, but we've added a couple of extra things on the right-hand side. So this is an ICOM 7300. This is your DC cable, and you can see there's a ring here. And the ring's got 1, 2, 3, 4, 5 turns to it. Plenty of filtering on the DC cable. We do the same thing on the coax coming out. All right, so it protects the outside braid of it. All right, Here we have the DIN cable. I believe this is the USB cable, and this one here is the send receive switch for the linear amplifier. So this particular kit has 3 snap-ons here, and it's got 2 rings, and we've sold thousands and thousands of these, and we have them for all different type of radios. Or you can just buy a generic kit with 3 of these in there and 2 rings and put it on your own radio. If you have more than one antenna hooked to it, then you're going to need a ring for every one of the antennas. And we have what they call deluxe kits versus what this one here is a standard kit with just 3 and 2. Now, if you really have a big noise problem, you can get rid of this ring here and you can put a little box in here. And this is called a coax noise filter. Basically, it's a whole bunch of ferrites in there with different mixes and different number of turns in order to get around 5,000 to 10,000 ohms of choking versus the 3,000 to 4,000 ohms out of this. Or saying it a different way, you pick up an extra 3 to 4 S units of noise reduction by using this little box. All right, we introduced this box, I think in Visalia, maybe 5 or 6 years ago. We sold over 10,000 of them. They're so popular. They're cheap. They're $60, and they just work like a champ. We make them for low frequency. We make them for VHF, and we also make them for HF. And with different connectors, we have them even for cable TV boxes with F connectors on them, because you have coax for your cable boxes too. And in this case, we have 4 different snap-ons here, 1, 2, 3, 4, and a ring, and then we have this one here. So this is what they call a deluxe kit, and we have it for all different types of transceiver. You can actually go on our website, put in your transceiver ID, an ICOM 7300 or a Yaesu 991, and generally there'll be a solution kit that pops up, which is designed essentially for that radio. And if you don't find it, you just use the generic kit, and that'll work too. On the other hand, if you have a linear amplifier, and this is a Meritron 811, I believe, and I think this is an SP220, but the concept's exactly the same. You have a AC power line coming in. In this case, you have to put a big snap-on there with a 1-inch hole and put it through 3 or 4 times. You have your relay cable down here. You have your RF input. So you can see there's a ring here. And then this is your RF out of the linear amplifier, again, through a big snap-on. In this case, it's got 3 turns going through it, so it's plenty of reduction. And this is the same one over here for an SP220. If you have some of the fancier linear amplifiers like the SPEs or one with multiple antennas, PW1s, those types of things, with multiple antennas and antenna tuners built into them, we have kits for those too. They just have more snap-ons for the multiple antennas. And sometimes you have 2 radios that can go into them too. So you have to have additional snap-ons for all the radios and stuff. So we have those available. So now let's talk a little bit about coax lines. This is a real problem. And basically, you want to stop the transmit RFI current on the coax braid. All right. I'm going to start out by saying that coax has got 3 conductors. All right. A lot of people don't know that, but coax has got 3 conductors. There's a center conductor, and there's an outside piece of metal called the braid. All right. That outside piece of metal is one piece of metal, but because of an electronic effect called skin effect, there's a current on the inside of the braid, which is separate from the current that's on the outside of the braid. All right. So there's actually 3 conductors. Ferrite only works on the outside current. It does not affect the inside current. That's good. It'll stop the noise on the outside current or RFI, but it will have no effect on the signal that's going up and down the middle. And this is true of no matter whether it's 75 ohm cable or 100 ohm cable or 52 ohm cable, or whether it's a RG6 or 213 or RG8X, the principle is exactly the same no matter what the cable is. All coax fed antennas have a problem with that outside braid, that outside conductor. That causes more RFI issues than anything else. And if you don't take care of that problem, what happens is your dipole becomes a tripole, or your vertical becomes your unipole, or vertical becomes a dipole. Because guess what? the coax becomes part of the antenna. You're transmitting, you think it's all going out the dipole, but it isn't. Part of it's going all the way back down to your radio, and that coax may be closer to your house, and that is causing the interference, even if your antenna is, 500 feet away. So you have to solve that problem, and we're going to show you how to do that. Right. So here's the diagram you've probably seen before if you've been reading the ARRL handbook, or you already know that coax has got 3 conductors. But I'm just going to go through it quickly. Your signal generally, let's just pretend this is a dipole. There's one arm here, one arm here. And this is your transmitter down here. And you're transmitting a signal up through here. All right. So at any one time, that's going to be plus, and then the inside is going to be minus, and they'll switch back and forth at 7 megahertz if it's a 40-meter signal, for example. But however, when this current is going up the inside of the coax, it's got a choice right at this point. It says, do I go up and do I stay on one side of the dipole, or do I go back down this extra path right here? All right. So on a regular dipole, the impedance is roughly 50 to 75 ohms, right? So you've got 37.5 ohms here, you got 37.5 ohms here. And if this is less than 37, then the current's going to be split and go down this way, unless you put a stop sign around here. And that stop sign is called a choke. If that choke has got an impedance of roughly 500 to 1,000 ohms, guess what? The current will follow the lowest impedance, and it will stop here. It will basically not go anywhere. All right. So that's the purpose of a choke, and that is true on transmit. All right. We'll show you some practical applications of that. But let's say you don't put a choke there. If you only had 1% of the power coming back and 99% going on here, which is typical, and if you were running 1,500 watts, you got 2.75 watts coming back down this way. Well, that's plenty to cause interference on a lot of different electrical devices. If you're running 100 watts, you'd only have about not quite a watt coming down here. Or if you're running, if you have old coax or something like that, it's been up for many years, you may have 5 or 10% of your current coming back at you. All right. All this is really easy to solve. And it's very inexpensive, but you have to realize you have a problem in order to know how to fix it. All right, so let's look at a typical diagram here. This is a coax antenna system. This is on the left-hand side, you have a transmit antenna. Over here, you have a coax line going all the way back to your transceiver. And if you want to stop the RFI from coming back down the coax, all right, if you don't do that, what happens is the coax radiates. That's what these little arrows here are on the top. It radiates and gets into things. Could cause issues, all right? So what you do is you put a stop sign here, and that's called a choke. The choke is a stop sign right here, and that choke prevents the current from coming back, going along here and radiating. It absolutely stops it, okay? And the higher the impedance of the choke, the better it works. This particular one here is good for almost 48 dB. Saying that another way, that's about 8 S units of noise reduction or transmit RFI reduction. Now, I'm just going to give you a little hint of what the opposite is if you put a choke down at the other end. All right. Just guess what? If you had some noise interference out here, and that noise interference is radiating through the air, and it gets into your coax braid, what'll happen is it'll induce a current called noise, which goes right to your radio. And when you screw in your coax braid, your coax to your radio, not only does the signal come down the center, it then adds any noise that the outside connects. So you would put a coax noise filter down here to stop that noise that's being picked up on the outside braid between wherever you have this choke or wherever the antenna is, all the way back to your radio. And we'll talk specifically about how to do that. It's pretty easy to do it, and it's very, very effective. That's why we sold 10,000 of those things. They work really well. Okay, so what are the technical requirements? And again, before you buy any choke, and there's so many chokes on the market now where they do not give you specs, all right? You buy a high Q Balun, or you buy a W2DU or any of those that says, hey, it works 1 to 300 megahertz, no specs. It doesn't tell you how well it works, all right? Or if you use one of these long pieces of PVC and you wind pieces of coax around it, They only work on one band. They don't on one frequency. They don't, because they're tuned parallel circuits. They don't work on a broad band. So what we did a long time ago is we designed chokes that work from this case. We'll just take this little small one. We start at 1 megahertz, we go all the way up to 30 megahertz, and look at the impedance. It's almost 5,000 ohms all the way across. Dips a little bit here on 10 meters, but still it's very good. This bigger choke here, this is a 500 watt choke. This is a 3 kW choke. And this one's also got a static bleeder in it. It actually bleeds off the static to ground if you have it hooked up. It is typically about 5,000 ohms. And this one here goes out to 61 megahertz. In fact, if you follow this curve out, it goes out to 2 meters, although we only spec it for that amount of power up to 6 meters, right? Very, very good chokes, all right? Now, I'm going to give you the same chokes, but I'm going to change the way we look at the graph to put it in more easy to understand terms. If we take those same numbers and we put them in how much common mode is suppressed, how much of that noise is suppressed, or how much of the RFI is suppressed, you'll see that over the frequency range, all the way, and this one goes up to 6 meters, we're down to about 38 dB here, and we're down to 49 dB on this one here. So if you were to put one of these at the receive end, 49 dB is 8, what's that, 8 times 6 is 48, that's 8 S units of common mode noise reduction. And over here, it's roughly not quite 5 S units. All right, and it's broadband. It's over the whole frequency range here, all the way from to 6 meters, all the way down to 160. All right, just it's really a nice nice product. All right, and it works on transmit or it works on receive, both ways. Don't buy chokes without any specs, unless you know the specs, unless you know the frequency range, and unless you either know the reduction ratio, it's called the common mode reduction ratio, or unless they give it to you in ohms. All right, if you don't have either one of those two, again, it's like buying a resistor with no values on it. All right, or no power specs. You don't know how much power, where it works the best, or whatever. All right, so here's some examples, on the other hand, of some very inexpensive simple feed line chokes that you can use. The specs aren't quite as good. All right, they're only good for about 30 dB, but still that's better than nothing. And these are $10 solutions. This is a simple ring. This is a dipole. This was a 30-meter dipole I think I had, and I put 5 turns through that. I just hung it right here from the dipole. Simple dipole choke, cost $10, and it's good for roughly about 18 to 20 dB. We also sell these here, which are we call them jumper chokes, and you can jumper these right to your dipole or your off-center fed or your vertical or whatever, and they provide about 32 dB. Pretty good, and they're only about $30. So it's not expensive to put these things on, but they can be very, very effective. Or you can buy the larger ones and get down to another, almost 50 dB on these things. Let's talk a little bit about the multi-bead chokes to put those in perspective now. All right. Remember before we had the 5 bead, the 10 bead, and the 15 bead. So here's that same thing we're not doing a resistance here, we're doing common mode reduction. So a 5 bead typically, and this goes out to past 6 meters. This is 1 megahertz all the way out to 6 meters. 5 beads good for about, the minimum is about, looks like 15, 10 beads is 21, and 26 dB here at rough in the ham bands. It's a little bit more outside the ham bands, but in the ham bands, it's good for about 26 dB or about 4 S units, right? And they're less expensive. They come in all different sizes, a quarter, 3/8, half, 3/4, and 1. And they're either snap-on or slip-on. And basically, by the way, there's not much difference between a snap-on and a slip-on in terms of RFI ability, but in cost, the slip-ons are a little bit cheaper than the snap-ons. But RFI-wise, they're almost identical in how they work. Okay, so what you want to do is, and here's a comparison. This is the same that we just saw: the 5 bead, the 10 bead, and the 15 bead. And that was in mix 31. But if you look at mix 75, remember that's the one for the low bands, you'll see that they're much better down here at the low bands. And when you get up just about to 80 meters, then the other one is a little bit better. The curve is lower. So if you have AM broadcast issues, these are perfect for AM broadcast issues. Or if you have noise on the 630 meter band, the 160 meter band, or even the 80 meter band, these are the way to go. They're also very good for anything that has a switching power supply. Wallworks, for example, you would use a Mix 75. And those work very well. So this is just a comparison about those. So you have to know your frequency. If you got a problem at 20 meters, you wouldn't even consider Mix 75 because it's way up here, but you want something that's lower. You want something down in this range. You'd use a Mix 31 for sure. Okay, let's go over to RFI kits here. Again, we come back to my lovely ex-wife. And our goal is to minimize RFI transmit to any electronic devices in your homes. And so we've had this question a million times, and the neighbor strategy is usually pretty simple. We'll just stop the source by choking you. And if you're not on the air, then it's not going to be a problem. All right. But the ham strategy is a little bit different. We'd like to stay on the air. We'd like to keep our neighbors happy. Right. So again, you have to know the source, the path, and the victim. In other words, how's it getting into your neighbors or your own devices? There's got to be a way to do that. So first of all, you clean up your own shack first. You put those RFI kits on the transceivers and the linears. Make sure it's not getting out a wrong way or getting back into the AC power lines. And then you have to assess your neighbor's problem. All right. In some cases, it might be just a faulty device. They got a bad receiver. It may have old power supply in it. It's just causing all kinds of noise. It has nothing to do with you. It may not even be your problem. You may be away on vacation, or you may be not even turn on the radio, but because you got a big antenna, they're pointing the finger at you, right? And so it may be, but usually it's either a telephone or an HDTV or something, touch lamps, for example, which are real sensitive, something that's acting as a radio receiver with no filters in it because it doesn't know what to do with anything below 30 megahertz. You have to determine the frequency of the transmitter that's causing the problem. It may not be you. A lot of these new meters that they're putting on the water and the electricity and the propane, they cause noise. And they're usually a source of a problem into some of the consumer devices. Have nothing to do with you, but you've got the big antenna, so you're obviously the problem, right? So anyway, yes, it's the same procedure. You try and find the path. All right, am I on the air? And if I'm on the air, is it interfering with their signal, with their receiver, so to speak? So you choose an RFI kit to fit the frequency and the path. You choke the path, and then you test it again to make sure it's not you. Okay. So we have RFI solution kits for virtually every device in your house, and other ones. We have alarm system RFI kits. Alarm systems always have long wires. The new thermostats or the new fire control systems that are wired together and not wireless. Those long wires also act as great receiving antennas. Home theater RFI kits for the DVRs and everything else that we have hooked to our home theaters, multiple HDMI cables hooked to your radios, hooked to your receivers and stuff. Computer RFI, this is an example of a router. All the lines going into the router and the DC have to be isolated. Miscellaneous RFI, any type of plug, and there's lots of plugs that use the universal cable, but generally a Mix 31 or a Mix 75 on the AC power line will solve it. Garage door openers, you have your AC power line that plugs in the top of the roof, and all your control lines, they're usually 16 to 20 feet long. They pick up 20 meter RFI beautifully. I just tell you. Telephone DSL lines. Generally, what you want to do is, if you can, in some cases, depending upon the relationship with your neighbor, you can actually go over there and just put them on. Sometimes you can suggest that they go buy the kit and put it on themselves. But one thing you want to do is you never want to go in and modify their equipment. You don't want to put capacitors across the speaker lines, for example. Right? Yes, that works with the old tube and vacuum tube stuff, but it doesn't work with the new solid state amplifiers and things. And so, but you never want to go in and modify your neighbor's equipment, because it will never stop. There'll always be another noise or something. It has nothing to do with you. They're going to blame it on you, but they expect you to fix it. Just don't get into that trap. All right. So to RFI proof your transmissions, determine the frequency range, pick a kit, install a feed line choke on all antenna coax lines in your station with enough choking impedance at that frequency that you're using. So there'll be different ones for VHF than there would be for HF, for example. Put AC/DC power filters on the affected equipment, retest it, and consider additional filters. If you get lost, you can always call us. We've got guys on board here that have been doing this for years and usually can pinpoint the problem. All right, let's just spend a few minutes here on receive noise, because that's a big problem these days. We're going to talk a little bit about the coax noise filters and also how to identify other sources. All right, again, same procedure. Assess the source, the path, the victim for the RFI. Is it you causing it? Somebody else causing it? One way to do it is just start turning on and off all the electrical circuits in your house. Hit the switch box and see which one, or run your radio on a battery. Maybe it's coming in through the AC. You want to protect your victim, which is your receiver. And that's typically the coax lines, any wire that's going into ferrites and AC/DC cords, wall warts, ferrites on the radio to computer interface cables, for example. You want to eliminate or isolate the source. In other words, it's always better to get rid of the source than it is to protect the victim, right? Because then it goes away for all the other things. Generally, it's going to be an AC/DC power supply. It's going to be a coax line, or it's going to be an interconnect line. If you get stuck, give us a call. But I'm going to show you in the next slide here a simple way to determine whether ferrites will work at all. All right, and typically you get a lot of noise on your coax line. So here is the simple coax common mode noise test. All right. So if you have noise on your radio, if you unplug your coax completely, you just take out the whole plug, and if all the noise goes away, you know it's coming in on the coax. The question is it coming down the center, or is it coming on the outside, or a combination of the two? If the noise doesn't all go away, it goes from S6 to maybe S4 or S2 or something like that, doesn't go down to 0, then you got another cable going into your radio that's causing a problem. And you should start taking one cable out at a time until you can figure out what it is. All right. A lot of times it may be a bad switching power supply. Some of these old Astrons have been around for, 30, 40 years, and the caps go bad in them, and they've got all kinds of hash on them. And they work fine, but they're real noisy. And so it may be just by trying a different power supply or going on a battery to see if that's the issue. On the other hand, if you unplug the coax and it all goes down to 0 and you got nothing else, so now we got to decide, well, how's it getting on the coax? Real simple. You take the coax and you screw back the PL259 connector, you just put in the center pin, and you measure the noise level, whatever it is, S2, S3, whatever. Now you screw in the outside part and see if the noise level changes. If it goes up, the ferrites will take care of that difference, right? If it was S2 to begin with just the center pin, and it goes up to S5, S6, S10, whatever it happens to be, ferrites can be used to suppress that down. And the bigger the resistance, or the bigger the common mode reduction ratio, the more that it goes down. So if it was a 48 dB filter, it would do much better than a 20 dB filter, for example, right? If you get no change, that means your noise in general is coming down the center of the coax. And no matter how many ferrites you put on your coax, it ain't going to do any good at all. All right. You have to find where the source is and how it's affecting and getting into your antenna per se, because it's coming down that line. All right. Now let's go to one more quick understanding here. So this is the diagram that you saw before. The concept here is you have a noise sources out here. They're getting onto the coax braid. They're coming into the transceiver, and you put a stop sign at the radio end. We call them coax noise filters just because it's easier to describe the concept. And typically you want those at least 3,000 ohms, or at least 20 dB of rejection ratio to be to have a measurable effect. In other words, you want it to go down a couple S units. No sense doing something that only goes down a half a S units because you'll have that much variation just in the signal sometimes. Okay, so how do you install these things and where do you install them? Here's a diagram of a transceiver, a noise filter, a linear amplifier, antenna tuner, antenna switch, multiple noise filters out here, and then multiple chokes out here for every one of the antennas. The chokes out here are to keep the RF on the antenna so that it doesn't come back down the braid and go all the way back down the radio through this. The chokes right here are to isolate this braid from that braid from that braid. And we'll talk about that in a second. This is the antenna switch problem. This is the antenna switch right here. Antenna tuner, obviously you should have a good ground system between all of these things, short as possible. And in a lot of cases, when you're transmitting from your transceiver into your linear amplifier, you will get some feedback coming back this way. So I generally recommend you put a noise filter in there too, and that'll just prevent anything coming back this way through a common ground system that's not quite equal amongst them all. Okay, let's talk a little bit about the antenna switch problem. This is an example of an antenna switch. This one's only got two cables on it, one for each antenna. If you put the noise filter in the common line, all right, it's going to filter between the switch and the radio, all right? But the switches, most of the switches on the markets today only switch the center conductors. They don't switch the braids. So at any one time, if you think about it, you've got two pieces of coax cable in here. You've got two braids connected together and you selected one center. So you've got at any one time, 3 antennas, always, unless you isolate the braids from each other, right? So if you put the noise filter on this side, you still got 3 antennas. If you put the noise filter on this side before it gets to the switch, before they can share their ground, or if they share their ground, it doesn't see all the noise that's coming in on that braid for the one you didn't select. Here's an example. I've got 3 acres and I've got antennas 500 feet apart. And I have one antenna that's next to an AC power line. It's a 40-meter vertical loop. And I've got a log periodic of 500 feet away. And if I originally had a switch with, I think, 5 antennas on it. And what was happening was the braid of the coax of the one that was closest to the power lines was coming in, and it was killing me on what I was trying to listen to the log periodic. And it was the darn braid. As soon as I put a choke in that line before the antenna switch, and I have that on all my antennas now, that noise completely went away because the braid here is isolated. So when you actually connect the switch on this side, you only get the center and you only get what's coming in through the inside. The braid is actually, this is a stop sign for the braid. It does not connect to the common. All right. Worst case is you put it over here on the common, but you still have all the braids connected together. And believe me, it makes a big difference. How do you know the difference? You perform the same test on the switch as you did, remember, with the transceiver. You go back and you do the same test with each one on your antenna switch. See if that outside braid is causing the problem. Or an outside braid of an antenna that you're not connected to is causing a problem. If it is, or if it's increasing the noise, then you need a choke on there. And the choke should be equal to the power that's going through it. These happen to be 500 watts, but you can use the tubes here like I did up here. I have 6 antennas on my switches. They're electronic switches, and each one's got one of these large tubes on it. And I virtually have no noise whatsoever. Okay. Different types of noise filters. Again, the 5-bead, you can do the simple choke, and it's got basically 2 to 4 S units. These here are about 1 to 2 S units with either 5, 10, or 15 beads. And the little box here has got roughly 3 to 6 S units. All right. So you just have to pick the one that meets your power requirements, meets your budget, and also can be connected into the system that you have, right? Coax noise filters, again, the same. This is just a graph for the same thing, about not quite 40 dB. And that's about 5S units of common mode noise. That's the noise on the outside braid. Now, in a similar manner, we do the same thing with DC power supplies. This is an AC one. You've seen that picture many times. Here's a large one. This has got 4-aught cable on it. This was on a 50-foot boat that I had in a big inverter, and it absolutely blocked all the inverter noise out. It was absolutely great. Here's 2-3 turns, and this is a dryer plug, and it's got 2-3 turn ones in series. So these add up in series, and these are 9 times what an original single turn would be. This is a large 3-inch ID. This is a cable for a generator, for example. Large plug for that. We try not to take off the plugs because it's just more cumbersome. We try and pick a ferrite with a big enough hole so you can put it through enough times to make it work. If you have a touch lamp, I'll just tell you the touch lamp solution right now. You use 2 mix 75s, you put 2 in series with 12 turns each. That will solve that problem. And it took me a year to figure that one out because I'm a big 160/80 guy and my wife sleeps during the day and part of the night. And I tell you, it took forever to fix that. She would not give up that touch lamp that her grandmother had given her. So had to solve the problem, but that's the problem. Likewise, if you have a switching power supply, a lot of the new power supplies are switching power supplies below 2 megahertz. Remember, mix 75. We actually have a kit called Rfi-S switch mode power supply that has 2 mix 75s in there. Solves that problem wonderfully. And it also works pretty good on linear power supplies, although they're not quite as noisy. If you have wall warts, any type of wall wart, you're plugging something in, and everything we got these days, from routers to DSLs to computer systems, or HDMI systems, have these types of wall warts. We sell them in 5 and 10s, and these are mix 77, not 75, but the specs are identical. But mix 75 isn't made in small rings, but mix 77 is, and they're virtually identical. They've been out a little bit longer than the mix 75s. If you're a newbie to all this and you don't know anything about this, I'll tell you the best thing to buy is the 1/2-inch snap-ons and the mix 30, and both in mix 31, and then the rings here. And with like all of our things that we have, if you buy 9 in a 10-pack, you get basically you're buying 9 to get 1 free. And until the end of the year, you can use a discount code called newbie, NEWBIE. You get 10% off all your orders. And we have free shipping over any orders over $100 anyway. So we'll ship them anywhere in the United States for that. Or you can go down to HRO. HRO sells these. They sell them in combo packs. And we also sell them direct and to some extent on eBay too. So I'm going to give you a few questions here to see if you've been paying attention. I'll give you the answers also. And I'll go back, first of all, before I start the questions. Does anybody know what the I stands for in Ohm's law?
It's the German word for intensity.
Oh, absolutely. Very good. I'll buy you a drink next time I see you. It's intensity. Most people do not get that.
Actually, it's a French word.
Okay.
Intensité is what
Intensité.
the origin was.
Ah, okay. I'll buy you a drink too. With my $5,000 retainer fee, you see.
Yeah, right.
All right, so here's a simple question. What are the 2 best ways to increase the choking resistance of a ferrite filter? When I was doing this in front of a group, I'd always give them a little ring, a ferrite ring as a kind of a prize, but I can't do that here, but I can at least give you the questions and kind of make your mind think a little bit. The 2 best ways: use a high resistance wire and multiple turns on the bead. Well, no, the high resistance wire is not going to do any good. It's going to kill the signal at the same time. Use multiple turns and double shield coax. It doesn't make any difference if it's double shield, triple shield, quadruple shield. It's the outside braid part that acts as a single conductor. It doesn't make any difference if it's double shielded or not. It's the outside still acts as an individual conductor. So it doesn't make any difference. So multiple turns, double shielded, triple shielded, that won't do anything. Use multiple beads in series with multiple turns. And if you really think about it, use multiple mixes so that you can spread out the the variation. That is the correct answer. Use mix 31 and 75 beads in series with a single turn. Yeah, that works okay, but it's not nearly as good as the multiple beads and multiple turns. It works the best. So do it that way. If you needed to go from 100 kilohertz all the way up to 2 gigahertz, you put a mix 71, a mix 75, and also a mix 61, all with multiple turns on one piece of wire. Right, that would give you the full range. Okay, and there's only 4 questions, by the way. Prize question number 2 is mix 61 is used in which frequency range to suppress RFI common mode current? 1 to 300, 200 to 2 gigs, 150 to 5, 1 to 2000 of the CB band only. Anybody got a guess? Okay, it's mix 61 is the one for 200 to 2 gigs. That's the one that's the really high frequency stuff. Right. So if you're using it at 450 or 1.2 gigs, or you're doing some moon bound stuff or something like that, all you need is 1 turn because it's almost 1,000 ohms at those frequencies. Okay, number 3 is what's one of the best kept secrets in ham radio? All the DXers know this probably. Ladder line has more loss than coax. No, that's not true. A coax wound choke can cover all frequencies from 160 to 6 meters if the coax is long enough. I didn't really show the picture, but I used to have a slide here, and it showed, I think it was a 6-inch long piece, a 6-inch wide piece of PVC tubing with about 14 or 15 turns on it. And if you run the graph on that, it goes up at 7 megahertz and it comes down and it's about 500 kilohertz wide, and that's it. And you see a lot of the old articles in the magazines, they say, oh, just put 2 or 3 turns of coax or 5 turns or whatever it is, and it'll work for all bands. Well, the point of that whole conversation is with me is that it only works on one frequency. It's a parallel tuned circuit. And a parallel tuned circuit has an infinite impedance theoretically, but not practically, and it only works on one frequency. So if you had a 40 meter vertical and you put that choke on the 40 meter vertical, work fine on 40 meters. But if you are trying to work on multiple bands, won't work at all. Okay, all ferrites work on all frequencies, so you buy the cheapest, right? Go to Amazon or go to eBay, just buy the 20 for $9.95. Obviously, that's not right. Coax noise filters reduce common mode noise level in your receiver so you can hear more stations. All right. The DXers that Visalia, I put that product out, I think it was about 6 years ago. I had 100 of them on the table, and in 1 hour, they were all gone. I couldn't believe it. And since then, we've just sold thousands of them. Really a good product. That's the common mode noise filter, the 500 watt one, the little box, the $60 box. All extra class hams go to heaven. I wish that was true, and maybe we'll see if it is.
Well, there goes my reservation with Satan.
Okay, last question. You should all get this right. Which company is your best source for RFI solutions? All right. Obviously, that's Palomar. We've got a pretty good reputation out there for high quality stuff. And we're just talking about RFI tonight, but also give talks on end-fed antennas, off-center fed antennas, all sorts of different ones. And in fact, this talk and all the talks are up on the website. And you can see the PowerPoint. They're also in Adobe format, so you can print them out and look at them. And quite a few of them are on YouTube, and you can see the whole talks from A to Z. And if you guys got any questions, I'm going to stop the sharing now, and we'll go back and do some Q&A. You can ask me any question. I'm here as long as you need me, and I'm all yours.
Hey, Bob, I want to make sure you don't take off, because I made you the host. So if you leave, we all have to leave. So if you can make me the host, that I'd appreciate.
Okay. Sure.
Hey, Bob, quick question.
Yeah.
What's the life of the ferrite itself? Case in point, I bought one of the MFJ current balance 1-to-1. It lasted about 6 months with 200 and 300 watts going through it. And then all of a sudden, the impedance of the whole darn choke changed and threw off the SWR and everything else. Put a new balun on and it worked fine. Is that the deterioration of the ferrite itself with heat or something like that?
No, what happens is it's a hysteresis effect. And so you have to, once you if you put too much power in a ferrite, and if you don't put a lot excess power into it, it heats up. The wires actually heat up, and then it saturates. And then when it cools down, it should go back to where it was, unless you put so much power through it that it realigns all the little domains in there and absolutely just makes it useless. Now, one thing, go ahead.
They spec'd it at 1.5 kW and only about 600 CW constant current. And that was running more than 350 watts.
Yeah, I was just going to make my next comment was, now you have to look at the specs. And I will tell you, from a practical standpoint, MFJ specs assume a 5% duty cycle.
Oh, jeez.
All right. So their sideband is a 5% duty cycle. So if they rate something for 1500 watts,
yeah,
they assume that it's 75 watts continuous. Right.
That makes sense.
Yeah. Our 5 kW ones, I run 1500 watts FT8 through it all the time.
Yeah.
I'm a contester. And so all of our stuff is spec'd for pretty high. You can't run 1500 watts through our 1500 watt ones, but you can run 800 or 900 watts through it all day long and it won't affect it. And if you're a contester, you buy our 5K ones. They're not that much more expensive, and you can run really, 90% duty cycles for 24 hours and expect that it's actually going to carry you through the whole thing. But MFJ's specs are very, very conservative. And if you ever taken one apart, and I've taken just about all their stuff apart, you'll find that they use one little small bead, not much bigger than the size of my finger in some of those things. And whereas ours weigh 2 and 3 pounds, they're a lot heavier. They're a little bit more expensive. Obviously, we don't sell them for $29. We sell them for $89. But you can put everything in the kitchen sink through them. And our specs are wider. We go from 1 to 61 megahertz. And that's the same for our balance too. Our 4-to-1 or 2-to-1, we make them all the way up to, I think 64 to 1 balance. And they're so broadband because we don't use toroids in anything we do. We use beads for everything. You've probably seen linear amplifiers with the beads that are used for the outputs. And they're usually 2 beads or 4 beads or 6 beads right next to each other in columns. And they're only using 8 to 10 inches of wire to accomplish the same thing you would with the toroid. But the toroid would have, for example, a 9-to-1 would have 3 48-inch pieces of wire. The labor is much higher. The bandwidth is much smaller. And with ours, we use 15 inches of wire, and our bandwidth goes almost from 1 to 100 megahertz flat.
Yeah. What about the single ring with multiple turns of wire and so forth? That's the one I've got now, and it's lasted forever. And
yeah. Well, in general, ferrite. Let me go back. If you're using a ferrite for a balun, or if it's used for a 1-to-1, all right. On a 1-to-1 basis, the only thing the ferrite's working on is the common mode current.
Right.
It's not working on the current going through the center of the coax.
Right.
It's only working on the common mode current, right? And so, but on the other hand, a 2-to-1, a 4-to-1, a 6-to-1, 8-to-1, whatever the balun happens to be, the current is going through the ferrite.
That makes sense.
Right. The total current. So if you're running 1,000 watts, you got 1,000 watts of current going through there. And if you use too small a wire, the wire heats up. It heats up the ferrite. And in some cases, the ferrite will crack. Once it cracked, it's gone. All right. Most of the time, it just saturates. Your SWR goes to heck. You're running digital or whatever, and it's 1-to-1. You're fine. Then starting, it goes 2-to-1, 3-to-1, 4-to-1, and it goes terrible. It's really high. You let it cool down, and it usually goes back. But in some cases, it gets so hot it cracks the ferrite, and then the thing is no good whatsoever. On the other hand, the 1-to-1s, you can run a lot of power through that thing. You run 10,000 watts through a 5,000 watt one, and the only limitation is the size of the coax you're using for the transmission line. It's not a function of good because you don't have that much power in the common mode. That makes sense?
Oh, totally.
Yeah.
Appreciate it.
Yeah. Other questions? Any antenna questions? I'm here. So
just a quick question. When you put, I think I already know the answer to this, but when you put the tuner at the transceiver and then you run a long piece of coax out to the antenna and it's unbalanced coax going to a balanced antenna and you have your choke, don't you still get radiation on the on that piece of coax as part of the antenna?
Well, the current's going up through the center of the coax, right?
Right.
When it gets to the antenna, yes, it's going to split. If it's a dipole, it splits in half. And if the choke is good enough, in other words, it's got at least 1,000 ohms or more,
Yeah.
then you're not, the outside of the coax is not going to be part of the antenna, and everything will stay on the antenna.
Okay, good. Yeah,
Yeah.
that's what I kind of thought.
That's true. That's true of any coax fed antenna. If you're using ladder lines, it's a different theory. In fact, one of the best antennas is the old ZS6 BKW, it's a fancy G5RE. And that antenna is, 46 feet on each side, 41 feet of ladder line, and it's resonant on 5 bands.
Yeah.
And it's quiet, except you can't use them in the rain. That's the only problem. But it's a
Yeah.
wonderful antenna.
In California, that's not a problem.
No, particularly down here. But I was on the net this weekend up in the swap net, I guess, on 40 meters, and they had 6 to 8 inches of rain and mudslides all over the place. But down here, I clocked a half of an inch, and that was it down here in
That's
St.
it. It dries in 20 minutes.
Yep.
So
Yeah,
Bob, I have a question.
sure.
How effective is turning your coax cable 5 or 7 loops before you connect it to the antenna?
Well, essentially, yeah. Let's go back. Let's go back to the theory for a second. When coax has got inductance, if you make turns in it, and it's also got about 28 picofarads per foot. All right. So when you're basically making a coil, all right, and if you make a nice one so that they're next to each other rather than overlapping, you essentially have a parallel tuned circuit. You have inductance and you have capacitance. Well, a parallel tuned circuit will have a certain resonant frequency, right? And that resonant frequency, because it's a parallel tuned circuit, will be high. It might be 5,000, 10,000, 15,000 ohms, but it's only good at that frequency. You see? So you can actually have a 1 band, in some cases, maybe a 2-band choke if the bands are close, like 10 and 12 or 12 and 15 or something like that. It can be wide enough to do both of them, but it won't be very broad band because the peak is very peaky. It's like a Matterhorn. It's not like a plateau. Like ours are like a plateau. They're very wide, you see, but that one is very narrow, and it's only good for that frequency, plus or minus about 0.5 megahertz. Right. And so if they're single band, yeah, they work fine. The problem is that most people change the diameter, they change the number of turns, and they really don't know what frequency it's resonant at. So really what happens is it's just extra wasted cable for the most part.
Okay.
Did I answer your question?
Yeah, it did, I believe. And how about the other question I had is how weatherproof are your chokes and filters?
Well, you can leave ferrite out even unprotected in their little plastic cases.
Yeah.
Virtually forever. You can throw water on them and it's not going to affect them whatsoever.
Okay, good to know.
I mean, some of the beads we put in shrink wrap because it just looks nice.
Yeah.
But in fact, you don't have to. You can actually just snap them on and just leave them there, and they'll be just fine. Sun deterioration of the outside plastic is more of a problem than the actual ferrite material itself.
Okay.
Yep.
Good.
Okay, I have a question on infeds.
Sure.
I'm looking at them. Is there an advantage between, say, the 9-to-1 and the 49-to-1? Or what do you recommend?
Okay. So there's 2 types of infeds, right? There's an infed half wave, right? Which means it's got to be a half wave long at the lowest frequency. So it would be, for example, 40 meters would be 66 feet long, right? And at 66 feet long, if you feed it at the end, all right, if you feed a dipole in the center, it's about 50 ohms, right? And it's what they call current fed. It's fed at a current minimum, a voltage minimum. But on the ends of a dipole, right, if it's a half wavelength long or a harmonic of that 20 meters, for example, is voltage fed, right? Voltage fed means it's got high voltage there. And that's why high voltage, if you remember Ohm's law, means you got high impedance. And a high impedance, what's a high impedance? A high impedance is 2,500 ohms, 2,000 to 3,000 ohms. So in order to get that back down to 50, you have to have a 49-to-1, right? 50-to-1 essentially. All right. However, on the other side of that 50-to-1 at the feed point of the antenna, there's 300 or 400 volts. Understand that. So when you put these end feds up, make sure you don't have that next to kids or animals or pets or anything, because there's high voltage there. That's one type of end fed. The end feds in general are only good for the harmonics with 40 meters, 20 meters, 10 meters. Now, if you put an antenna tuner right next to it, the antenna tuner will make the radio happy, but the end fed is not, the efficiency goes to hell. Now, the second type of end fed, which is what we sell, all right, I'll just tell you my bias, is that is a non-resonant end fed. Now, a non-resonant end fed radiates just as well as a resonant end fed. However, it's resonant outside the ham bands. So what does that mean? That means that in the ham bands, the impedance at the end of that antenna is roughly 400 to 500 ohms on all frequencies. Not just 40, not just 20, not just 10, but on 40, 30, 17, 15, et cetera, et cetera, et cetera, if you pick the length right. And so a typical length would be 31, 55, 71, 92, 110, 155, 135. Those, if you pick those lengths, it turns out that the impedance at the end of the wire will be very close to 400 to 500 ohms. So if you put a 9-to-1 in there, guess what? Gee, now it matches 5 bands or 6 bands in the same 71 feet, but the guy's 66-footer doesn't match any bands. It only matches 3 or 4 bands, or 3 bands, 80, 40, and 20, or a 40, 20, and 10, for example. All right, without putting fancy coils and all the other stuff in it. And so you have more bands, shorter length, safer antenna. That's why the Jamboree on the Air, we sold thousands of those to the Jamboree on the Air Boy Scouts. We call it the bullet antenna because it looks like a big bullet. And in fact, they threw it over one of the branches at my house, and that's how it got its name. And it didn't break on the other side when it fell to the ground. And so it's good for 500 watts, that particular one. We make them up to 5,000, but and it's 71 feet and it weighs about 2 pounds. You put it in a backpack, you can deploy it, in about 2 minutes, 3 minutes. We use it at all the ham fests. We put a 20-foot vertical fiberglass pole. We put the feed point at the bottom. We run it up 20 feet and out to a cyclone fence. And we can work anybody we can hear with a ICOM 7300, which we take to the ham fest and stuff. So that antenna works really well, and it's much more versatile, I think, than the end-fed half waves. And it's more safer from a product liability standpoint, from our standpoint too. So you get more bands, virtually the same length, and it's easier to deploy, and you don't deal with the voltage issue. Long answer to a short question.
No, thank you. That's very informative.
Hey, Bob, question.
Yep.
What's your opinion on having the antenna itself resonance regarding inductive reactance, capacitive reactance resistance as a resonant circuit versus a tuner which makes the radio happy? What's your opinion on the actual resonance for receiving good DX?
Well, the question is are you tuning the coax or you're tuning the antenna?
You're tuning the antenna.
You're tuning the impedance at the end of the coax or the end of the transmission line is what you're doing. I've done, in fact, I think it's on the website. I run a vector network analyzer, and I've calibrated it several ways. One way, I have an antenna that's fed by a piece of coax 268 feet long. And I have run the VNA calibrated at the VNA itself, but I've also calibrated at the end of the coax. And I've run the SWRs on both of those, and they are significantly different. Because what happens is the coax, even though it's got a great choke on everything there, the radiation of it couples to the ground and other things. And so the SWR curves are a little bit different. They're not quite as deep. And your antenna tuner is essentially tuning the entire system to be resonant. Now, as far as radiation is concerned, they're similar, right? Whether you have an antenna tuner there or not. But in a lot of cases, if you took a 40-meter dipole and you put your antenna tuner on it and tried to work it on 30 meters, the efficiency I mean, your radio would be happy. The antenna tuner would tune it because it would tune out the inductance or the capacitance difference in that thing. But it wouldn't radiate worth a darn. It would radiate a lot less efficient than a regular 30-meter dipole, for example. Although it would be tuned just fine. Your radio, like I say, your radio would be happy. So what you want is something it's either broadband or it works with multiple bands where, you know, your SWR is typically less than 3 to 1, hopefully less than 2 to 1 naturally, without having to put a tuner in there. Our NFEDs typically are less than 2 to 1 from everything from about 40 meters up. And the longer they go, the better it is. All of our SWR curves for all the different lengths of our antennas, they're all on the website. You just look them up and say, okay, I want to work these bands. This is how long it has to be, or this is how much space I've got to make it work. They're used in attics. They're used around the perimeters of homeowners association houses. There's lots and lots of different ways, and they're friendly because you can zigzag them. Whereas your NFED half waves generally have to be pretty much straight line because of the way they're designed.
Yeah.
Because they're voltage fed too.
I've always believed that if the antenna is resonant, it produces an impedance at the feed point. Okay. Now, if that impedance is not 50 ohms, you can match that impedance to the coax and so forth. But I found out with the actual doing, I found out when the antenna is actually resonant, I receive better. I receive better DX way down in the mud, a lot better. Go ahead.
I agree with that. Resonant antennas generally receive better than non-resonant antennas in terms of that aspect of it. I haven't experienced that with our NFEDs. They are non-resonant in the ham bands, but they still are. They're still pretty good in terms of reception. Well, you know, you're buying a compromise and you're buying a piece of wire that you're trying to make work on 6 different bands or 7 different bands.
Yeah, right.
So, you know, it's not going to work on all bands the best, but guess what? It works on all bands, you know.
Yeah, it's a happy trade-off. That's
it's
true.
a happy trade-off, right? I mean, I would, if it's less than 2 to 1 SWR, which is only a 5% loss, who cares?
Right.
You know, if it's 2 to 1 across all those bands, I'm happy. I can work them all, you know.
Yeah, exactly.
Bob, I have a question.
Sure.
Yes, it's kind of follow-up to the question that Pete asked you regarding the creating loops with the coax. And
Yes.
I'm kind of new to this ham radio. Can you hear me all right?
Mm-hmm.
Yeah, okay. And so
Just needed a drink.
I'm mainly dealing with 2 meter. And so I'm using just on my antenna, it's a portable J-pole. And I'm using just, I'm not using any ferrites, just loops, just the way like Pete was explaining. And do I really need to use ferrites for the 2 meter?
Well, you see, you're using it on a single band.
Right.
And so the number of loops that you need, you know, you can just take a 1-inch piece of PVC, and I think it's 2 to 4 turns or 5 turns or something like that on the bottom of it. And that's pretty much tuned to 2 meters, you see. You know, if you were using it on 2 meters and 440, you got one of those combination J-poles, for example, it would only work on 1 band, you know.
Oh, so it won't work on 440 because I do use that same antenna for 440.
440. So the balun is only going to work, or the balun or the choke. A 1-to-1 balun and a choke are the same word are different words for the same thing. And so it won't work on both bands. I mean, they're harmonically related. So technically there should be some reaction, but in general, it's a parallel tuned circuit. But if you took 2 ferrites, all right, just 2 little snap-on ferrites and put them on your line, it would work on both bands. All right. So it's a $10 solution versus you know, playing with loops of coax.
So just using the loops, it just it doesn't cut it. You need to use that just like you.
Well, you're not getting any benefit of using the loops.
Right. Okay. Yeah, just the way you were explaining by using the ferrites, big enough hole and then just doing the.
Yeah, you know, see at those frequencies, the ferrites are 250 ohms a piece. So really, you need from 2 to 4 at the most. We sell an RFI. It's called a snap-on kit. a snap-on,
Right.
either quarter or half or whatever the size of your cable is, and it's -4. It only takes 4 ferrites to completely get you 1,000 ohms on those frequencies. And that's good up to almost 2 gigs. So doesn't take very much to do it. And it's a $15, $18 solution. So and you can transfer it to other antennas when you're done with that one, you see.
Okay, thank you very much.
Yeah,
Thanks.
you're welcome. Sure.
Hey, Bob,
Yeah.
when you go to bed at night, do you count ferrites jumping over the fence?
Yeah, I have a little ferrite. I have a little stuffed ferrite next to my bed. Yes. It's Freddie. His name is Freddie, by the way.
I got it. I figured.
And his wife is Fanny. And there's a little ferrite, and I can't remember Freddie Jr. I think it is.
Yeah.
My wife got me those for Christmas one year. Three different ferrites. So I dream about new antennas more than I do about ferrites these days.
Yeah, I hear you.
We've got a new off center fed with a vertical radiator, which is just kicking butt. It's just I've been using it for about 3 months to run all the nets on 80 meters and 40 meters, and it's just a really good antenna.
Yeah. Good stuff. Okie doke.
All right. Well, thank you, Bob. That was very good.
Oh, you're welcome. Yeah.
Very, very good.
One of our
Very
better
informative.
presentations, I would say.
Yeah, very informative.
All right. Well, I'm glad you guys learned something. So if I leave, are you guys gonna all fade out now if I'm the host?
Yeah, just
I'm
make,
sure we'll all be jumping on your website here pretty soon.
Okay. Well, it's always up 100%.
I
So
can make somebody else the host. This is
yeah,
Dave.
yeah. You can go ahead and do that before I leave. So I appreciate the opportunity, and like I say, it's on the website and stuff. Just look it up under presentations, and you can see the whole thing.
Hey, Bob, are you still working full-time, and are you consulting full-time and stuff?
No,
Oh, okay.
no, I stopped that about 10 years ago,
Oh, okay.
and I started this company, and I do this more than full time.
Yeah.
We got a lot of people working for us, but
Yeah,
I still love doing it. If you always have the choice, do what you love.
sure,
And,
absolutely.
it shows in the products that we have and the quality that we have. And if you're going to do it right. I'm over 70, so I got to do something,
Yeah.
right in my life. And this is one of them.
If you do what you love, it's not a job.
Not a job. No, it's enjoyable to talk to you guys and to talk to people all across the country and the world. I did a big one up in Canada too, and it's good to get the information out to everybody because it's simple. It's simple to solve these problems, and the problems are getting more and more and more diverse and with all the equipment that we got in our homes these days. So
Sure.
it's something we all got to deal with it.
The way you did this presentation, it shows that you really love what you do.
Thank you. Thank you.
Very good, Bob.
All right, guys, I'm going to take off. Been a pleasure. See you
Thank you.
later.
Thank
All
you.
right.
Thank you.
Now, if I can find where my mouse is. Okay. We'll see you. Bye-bye.
Ferrite took it.
DJ, you became host.
thank you.
Hey, just real quick, guys, this one's kind of going over time limit here, but do we have any news that's available for the club that we really need to talk about, or?
Just get those ballots in.
Yeah.
Do your
Okay, we
ballot.
still need the ballots, okay.
Yeah.
Okay, everybody turn in your ballots,
Thanks, Ed, for
even
running
though the slate's kind of full.
thanks for running the show, Ed. I really appreciate it. This is Dave. I
Hey, no
joined
problem, Dave.
late. Okay, thanks for that.
Pretty much Bob ran the whole thing anyhow. So.
Okay. It was pretty interesting. The part of it I did see, it was great.
He definitely knows his stuff, and it was
Yeah.
very, very
Oh, yeah.
informative, very good.
Really, really good.
Yeah.
I love the
Okay,
topic.
well, if we don't have anything else,
No.
go ahead and shut it down. So it's last chance. Anything for the club?
We definitely need to get somebody to run for director at large.
Yeah. Come on, somebody step up.
Ed,
All right. No, Ed's busy. He's the only one that works.
Hey,
Don't pick on Ed.
Hey, DJ, one comment on that. If nobody shows up, maybe we could do stuff like through yourself or whatever as a contributor to the director at large. In other words, somebody could contribute during the meeting, and he would only have to do it one time as opposed to doing it full time. And then just keep looking for contributors to find things that are of interest.
That's actually not a bad idea. Actually have somebody assigned to each month and just have one.
Yeah, and then
Yeah.
gives them
Maybe
time.
spread it out a little bit. That would be that if we can rig something like that, it'd be a good idea.
Yeah, I mean, I think you'd get more of a variety, and when the one person wouldn't feel like he's overloaded, as DJ knows very well.
Yeah.
Okay, but maybe that would work better than trying to find someone who's not really interested in it but accepts it, and then you know it's not as good quality as if you had contributors.
Yeah, it's hard to. I don't know. We'd probably have to change things a little bit. It's a position that normally has a person assigned to it. So
Yeah.
yeah, I don't know. I kind of agree with you, but I'm not sure how we could manage that.
I don't know. It's better than zero.
That's true. That's true. All right. Well, get those ballots in. I'm guilty of not filling out mine yet. So, but let's get our ballots in. All right.
Okay.
Ed, you gonna end this thing? You're the man.
Okay. It just turned, so I'll close it down at 2100. Thanks everybody for showing up, and
yeah,
hope you all
Yes.
enjoyed the presentation. I know I did. So,
Yeah, very
That
good.
was really good.
it was.
even though it went a little long there and we didn't get our break, I think
was worth
well
it.
worth it. So
Yeah.
Yeah.
Who needs a break?
Okay.
Thanks, guys.
all righty.
Okay.
I guess we'll all start dropping off then.
See you later. Take care.
All right, thanks guys.
Bye.
Thank you.